All right, let's look at composite functions. So that's another operation we can do that's special for functions. So the operation for that, it's like f composed with g. So it's almost like a multiplication dot, except it's got an open circle, whereas this is f times g. So this is times, and this one is composed with f composed with g. So composing functions, if you think back to our first day of class when we had our function machines, so we had one machine that we put in some value x and we got out a value and that came out to another value, and we had to input that into another machine and get another value. So if I put my x value into g first, the function for g, and then my output of g becomes my input of f, then my output, that after going through both machines, so x goes through both machines, it goes through g first, so that's the inside function, and then I took that output and I put it into f. So that's my output after going through both machines, and that is a composite function. So that is also written as f composed with g of x. So both those notations mean exactly the same thing. Please note that the order matters. If I put the x into g first and then f, then I'm going to get a different answer than if I had put it into f first and then g. You may remember that from that first day activity. So order matters. F composed with g is equal to f of g of x, and g composed with f is equal to g of f of x. So that order matters. It's the same order regardless if you use the composition or f of g of x notation, but that order is important. All right, now the domain's a little more complicated. The domain that I have to have the x be able to use that x, right? So I can't plug into something into this g in this example. In this machine example, I'm using that one right there. So f of g of x. I can't plug in that x if it's not in the domain of g. So one restriction is that it has to be in the domain of g. Even if it's not in the domain of f, I might be able to put it in g and then get a result that is in the domain of f. So that is possible. So what I'm going to do to figure out what the domain of the final function is look at the domain of g to make sure I can put x in there in the first place, and I'm going to union that with the domain of this function after it's been composed, so the result of the result function. I want to say the composition, but that's what we're finding the domain of, so kind of a play on words here. So let's look at what that looks like in an example. So in these two equations, these two functions, I'm going to find, let's do f composed with g in blue, and then we'll do g composed with f in purple. Let's start with the blue one. So f composed with g. So remember that this notation is the same as, it's abbreviation for this, and this is the same thing as f of g of x. And this parenthesis notation is a little more visual. G of x is the input that we're putting into f. So I'm actually going to highlight that in orange. This is this thing. So what I'm really doing is finding f of the 2 plus x. So replacing g of x with what g of x is, which is 2 plus x. Actually, I'm going to put that in orange. So my input is 2 plus x. So taking f of g of x, or f of 2 plus x, then I look at the f, which is 1 over x minus 3. And instead of x, I'm replacing that x with g of x, or 2 plus x. And then simplifying that, that's 2 plus x minus 3, so that gives me x minus 1. That's my composed function of f of g. And then to find the domain, remember I need to look at the original inside function. So I need to look at this function first. There's no restriction on that domain. That domain's all reals. And then I have to look at this function, and there is a restriction on this one. So I find that x cannot be equal to 1, or else then I'm going to get a 0 in the denominator. So that's my only domain restriction, which leaves me with the domain going from negative infinity all the way up to 1, not including 1, and then after 1 all the way to infinity. So there's my domain and my f of x. Okay, so I made some space to do down g of x. G of x, so that means I'm looking at g of f of x. And I'm plugging in f of x as the input. So f of x is 1 over x minus 3. So that's my input. So when I write g, this is g, so I have 2 plus the input. And the input is f of x. So when I write that, I get 2 plus, and f of x is 1 over x minus 3. And adding those together, I need to get a common denominator. So to get 2 as with a common denominator, I need to multiply by x minus 3 over x minus 3. Adding 1 over x minus 3, I get, let's see, what do I get? I'm going to distribute this 2, and I get 2x minus 6 plus 1 all over x minus 3, which I can combine the negative 6 and the positive 1, and I get 2x minus 5 over x minus 3. There's my final composite function of g of x, g of f. And my domain restrictions, let's see, I have to look at the inside function, which in this case is f of x. And that tells me that x cannot be equal to 3, or else that denominator would be 0. And I have to look at the composed function, which has that same restriction actually in this case. So again, x is not equal to 3. So my domain is going to be everything but the 3. So going from negative infinity all the way to 3, don't include the 3, and then up to infinity. All right, moving on to example 2. So starting with f of g, so remember this notation is shorthand for f of g of x, and that is shorthand for f of g of x, where g of x is the input into f. So g of x is 1 over x. I'm going to input that into f. So f is absolute value of x minus 1, leaving that parenthesis for the input, and that input is g of x, which is 1 over x, which equals let's get a common denominator in there, and we get 1 over x minus x over x, which gives me 1 minus x over x. And I think that's as simple as I'm going to get. And I still got the absolute values bars there. So there's my answer for f of x. F of g of x. And my domain restriction. So again, I have to look at the inside function, which is the g of x. So the domain restriction here is that x cannot be 0, and also the final result, which also has the same restriction of x is not going to be equal to 0. So my domain is everything but 0, so negative infinity to 0 without including 0, and all the way back up to infinity. And then g of f means I start with the g, which is 1, so g of f of x. And f of x is the absolute value of x minus 1. So I'm taking g of x minus 1, absolute value, which gives me, and g is 1 over x, and instead of x, I'm going to write the input of x, which is the absolute value of x minus 1. And that's as simple as I'm going to get with that one. So that's my composite of g of f. In the domain, again, I have to look at the inside function, so I have to look at f of x. There's no restrictions here, though. And the restriction on the result is that the absolute value of x minus 1 cannot be 0 because it's in the denominator. So for that to be 0, x would have to be equal to 1. So x cannot equal 1. So my domain is negative infinity all the way up to 1, not including 1, and then everything after 1. So everything but 1.